Hello, grade 9s, and welcome back. It's Mr. LaRusso here. We're now moving on to electricity, current, and voltage. Now, we're going to do something a little bit different, and this time I'm going to try to do something a little bit more interactive, and I will also include the link to what I'm using on this page over here. So we talked about static electricity, and the idea, and let's do a little refresher. An idea of static electricity is that you have a buildup of electric charge. So let's say, for example, we have some object here, and I have a couple of positive charges, and then we mix that up with some negative charges. And actually what I'm going to do is I'm going to change the colors here. I'm going to make positive charges red, and then our negative charges black. So with this object here, if you recall, we consider this to be neutral because we have equal number of positive charges to negative charges, and positive and negative charges are really electrons and protons. If I add a couple of extra electrons or negative charges, this thing has an overall negative charge. If I remove a bunch of electrons and I'm only left with 2, now we have a net charge of positive, specifically 2+. So this is what we talked about in terms of static electricity. Static electricity implies that there is no flow, but we want to talk about something called current electricity. So what is current electricity? Well, current electricity is the continuous flow of charges in a circuit. Now, we have to clarify a few things. Before, we used to think that electricity was a fluid. So our circuits are kind of a bit weird. So we want to talk about this. There was a historical error. It was historically believed that electricity was the flow of positive charge. And that's kind of still the same way that we actually work with circuits today. We still pretend that it's a flow of positive charges, when in reality, it's a flow of negative charge. And again, this all has to do with a mistake in history with Ben Franklin. Ben Franklin invented, or was part of those who invented the electrical standard before we actually knew what an electron was. So what I have here is a little diagram of a battery. All right. Now, on this battery, we have two sides. When you look at this battery, now I've only represented the negative charges here. So let's talk about how this would work here. If we look over here, the big idea is this: like charges repel. So negative charges don't like being with each other, so they're going to push on each other. So the closer they are, the stronger the force of repulsion. So if we put a bunch of negative charges in a tight area, these negative charges really are trying to get as far away from each other as possible. So as you can see, what they're trying to do is they're creating a bit of a pressure situation. They're pushing really, really hard on each other because they're trying to get away. Electrons don't like being near other electrons, but electrons are attracted to positive particles, protons. So let's take a look at my little example of my battery here. I didn't include the positives, but there are positive charges on both sides here. So they're just hidden. So let's take a look here. If you were an electron, which side of the battery would you prefer to be on in the current state? Do you want to be on this side or on this side? Well, from an electron's point of view, they like to be as far away from other electrons as possible. So when we take a look over here, this side has significantly fewer electrons. So what we now have is motivation. We have what we call electric pressure. We have a special name for electric pressure. Electric pressure is called the voltage. And this is basically how strong of a push there is to get these electrons to move from one side to the other. Well, we discovered this feature about electrons and electric charges and used them to our advantage. And that's how a battery operates. So on this side of the battery is considered to be the very negative side. So this would be the negative side of our battery. Where this over here, the conventions here, so this would be your negative side. Where this side of the battery is positive. Really what this means is that this side of the battery is more positive than this side of the battery. Or we could say this side is more negative than this side here. So the relative pressure is higher on this side. So the electrons, they want to flow in this direction here. And what they can do for us is that they can go through and do work for us. What I've drawn here is a symbol of a resistor, but really this means any type of load. So something like this could be a flashlight, or it could be your iPhone or Android if you prefer, or your laptop. Anything that requires electricity, that's what this represents. And the battery is supplying enough electric flow to make this operate. So what we're doing is we're actually putting these electrons to work. And again, if you think of this in the same way Ben Franklin thought, he thought of this as like water movement. So kind of similar to the way an hydroelectric dam works. So let's say let's draw a little example. So let's say we got a little river, and then we have got some falls here, and then it goes flat here. So we take a look at Niagara Falls, for example. So with Niagara Falls, right, which is the first hydroelectric dam that we had, the water flows over the falls, falls down, and then continues on towards the ocean. All right. Now, so we got water flow in this direction here. Well, what we discovered, and we've been using this technology for many years, is we have, before electricity, we used to make mills to capture the water to actually run sawmills or to grind flour, et cetera, et cetera. But in the beginning of the 20th century, we created a hydroelectric dam. And what they did is they built a pipe that drained some of the water away from the falls. And inside here, they put a turbine to catch the water flow. So when this water would flow here with high pressure, it would cause the turbine to turn around, therefore generating electricity. Well, we used water pressure to make electricity. Well, a battery uses electricity to run other machinery. It's the same idea, and it's interesting that they used water flow to really be an analogy for electricity flow, because they really do operate in the same kind of way. When you have a difference in pressure, you can get things to move. Okay, so now, as the electricity flows, eventually things are going to start to change here. And the reason being is that as the electrons move over, we get electrons coming over this side, but every time an electron comes over here, we lose one on this side. Add another one here, lose one on this side. Add another one here, and we continue to lose charges on this side. Well, what's happening then is now this side is becoming more negative, and this side is becoming less negative. And eventually, what happens is they equalize. And when they equalize, we stop getting electrical flow. And that's when your battery is dead. And that's when you either have to replace the battery or get a new one. So this is the current look or understanding of how electricity flows. Well, how did they do it in Ben Franklin's day? And how do circuits still work? Well, here's the confusing thing. Ben Franklin and everyone else thought it was a flow of positive charge, and they used the letter I, right, to represent current flow. Even the word current comes from the motion of fluids, like water, like a water current, or we consider electrical current. So in this case, it was thought that the positive charges moved around and continued to flow over to the other side. Well, how can we have two different ideas meaning the same thing? Well, basically, it's the same idea. And here's what I mean. From this perspective, this side is becoming less. So if we talk about positive charge, this side becomes less positive. And then this side becomes more positive, which really is the same thing as saying this side is more negative and this side is less negative. So effectively, it doesn't make a difference whether you look at it as a flow of imaginary positive charge or if you see the real flow of negative charges moving in the opposite direction. Basically, it works out exactly the same way. So we traditionally still use this idea of a positive flow of charge because working with positive numbers is easier than working with negative numbers. Again, the only reason why we have this confusion is because we came up with this standard before we discovered the electron. And that's just, part of history. That's just an accident of history. Because had we discovered the electron, we never would have given the electron a negative charge. An electron would have been given a positive charge, and the proton would have been considered negative. Then it would be very easy to understand. But because of this, early misunderstanding of the science, we're sort of stuck with it. And that's always a bit challenging for young students. It was actually challenging for me even as I was getting older until I really dug deeper into the history of all of this. All right, so let's before we get into this, I'm going to actually do an animated version. So over here, I have a little demonstration to help us take a look at how these electric circuits operate. So we're going to start off with a couple of these symbols here. So the first thing I'm going to put is a battery. Now, when we look at this, I'm going to explain a few things. This is considered the positive side of the battery, and over here, this is the negative side of the battery. All right. So now we're going to add some wires here. All right. And then I'm going to put in a light bulb. I'm going to draw it like this. Help me with my analogy here. And here we have a flow of electricity. All right, so now what I like to do is I like to look at this as, and I call this my water slide analogy. Actually, all right, so I drew it a little bit different so we can see it. So what I have here is I've kind of made it look like a water slide. Now imagine this being, the battery being your ladder. And the ladder, when you climb it, gives you greater height. And we consider that to be energy, gives you more energy. Now, the higher you go, the faster you're going to go down here, which means that the higher the voltage of your battery, the faster we're going to get flow. So imagine you climb this, and when you get to the top, you're going to start to flow down here. So, and actually what I'm going to do is I'm going to do one more modification. I'm going to get rid of that wire. Just going to draw it like this, because then what I'm going to do is I'm going to add another battery here. All right, so now, right now, we have a flow of electricity, and our flow of electricity is in this direction. But this is a flow of imaginary positive charge. This is the conventional way of looking at it. But what's actually happening in real life, and if we click on over here, what's actually happening are the electrons are going in the opposite direction. And again, the reason why we have it backwards is because of that mistake back in the day of Ben Franklin. So let's go back to conventional, because that's the way most circuits are designed, is that we pretend that it's a flow of positive charge, but you just have to remember that it's really electrons going the other direction. Doesn't make a difference for how the circuit works, but it's important that we know that distinction. So now what we can see here, I'm going to bring in something called a voltmeter. Now, the voltmeter, the black lead is designed to go onto the negative side, and the other lead is to go on the positive side. So this says we have 9 volts, all right? So the question is, what is meant by a volt? Well, a volt is a measurement of energy per charge. So when we talk about a volt, it's equal to the amount of energy we have over the number of charges that we have. Let's think of a volt kind of like food calories, all right? So it's kind of this idea of energy density. Let's think about the difference between something like a chocolate bar versus celery, all right? A chocolate bar has more energy in it than celery does, which is why, like, if you have too many chocolate bars, you gain a little bit extra weight. For the same amount of weight, celery has a lot less energy. So voltage, the way we think of voltage is the amount of energy density that we have. So a high voltage food would be like sugary treats or high in calorie content stuff. Low voltage foods would be things like celery and lettuce, and these are things that have fewer calories per weight. Things that have higher calories per weight, we would consider that higher voltage because it gives you more energy. So think of that in mind, right? So right now we have 9 volts is the amount of energy density that we have. So this is just, a medium sort of amount of calories here. So we've got the voltage and it's flowing, causing the electricity to flow. Now, the voltage, another way to look at it is like pressure. So we have a pressure of 9 volts. Well, what happens if we decide to add another battery here. All right, so now what I'm going to do is I'm going to take my little meter away and I'm going to break this apart. And now what I'm going to do is I'm going to add another battery. And let's see if it's going to let me get it a little straighter there. Okay, so now I've doubled the size of my ladder here for my water slide. So if I double the size of my ladder here for the water slide, what should happen in terms of the flow? Well, as you can see, the flow is much faster. So now we're reaching a greater electrical height, or we have more energy, or if you prefer, more pressure. So now I've got two of them. So now this is 18 volts. Now it's much easier to sort of imagine this as instead of 18 volts, we can talk about 18 feet of height. So the higher you go, the faster you're going to slide down. A bigger hill means greater speed. Well, with electricity, the hill size is associated with the voltage. So the more voltage we have on our power source, the faster the flow of electricity is going to be. Let's add a third battery. So if we add a third battery, things should get even crazier now. So now when we add this third battery, the flow is even greater. So I'm going to add something that measures current. Current is the speed at which the electric flow is occurring. The higher the current, the faster the flow. And this would be like turning on your tap. If you turn on your tap a little bit, you have low flow or low current. You turn on your tap full, you get a high current. And remember, when you turn on your tap, you're actually adjusting the pressure. So the more you open it up, the faster it's going to flow. All right, so now let's break this apart again. So we got the low flow. So here it is with just the one battery. Oops, 9 volts. Here we are with 18 volts, and notice that the current doubled. And now we are here with 3 batteries, and the current has tripled. Okay, remove these. Okay, so now I've cleared the tablet. So let's take a look what happened. So let's see if we can figure out what's going to happen if we actually make the path with more light bulbs here. All right, so let's start off again. We'll do our 2 batteries. We'll add a wire. We'll add a light bulb. All right, so now what I'm drawing is something called a circuit. And we usually draw them in a rectangular fashion like I am here. Now, this is what they look like in real life, but this is using the actual symbols. So a symbol for a battery looks like this, where the short side is the negative side and the long side is the positive side. All right, so we'll go back to this mode here so we can see that our light bulb is lit up. And this is the same thing that we had before. So now what I want to do here is I want to add another light bulb. If I add another light bulb, so I'm going to break it apart here. And of course, do you see how the electricity stops flowing? Well, the reason why the electricity stops flowing is that we have a break in the path. There's nowhere for the electricity to go because we broke it. Now I'm going to add my light bulb. And then as soon as I make contact, we have flow. But look what happened to the speed of the flow. All right, so now I'm going to put this here. Now I'm going to break this apart again. I'm going to remove this, and then I'm going to reattach it. Notice the current. Break it apart. Do you see what happened? The current is cut in half now. Well, what occurred? Why is that? All right, so what we're going to do here is I'm going to show you what I like to call, again, my water slide analogy. So let's go back to the other sheet here. So let's consider a ladder. And this ladder is going to be our battery. I'm kind of drawing it like a battery here. So batteries are drawn like this, negative side, positive side. All right, so we climb up our ladder. Now, this part is the plateau. And then we go down the slide part. And on the slide, we hit an area of resistance. And then we reach down to the bottom again. So if this is sort of your water slide analogy, and let's say you are a positive charge, you climb up the ladder, and then you move down, and then you go down, and you slide, and you continue this loop. So imagine a bunch of kids climbing this ladder and sliding down the water slide. Well, what would happen is if we actually made the water slide have 2 slow sections. Well, if I added another slow section, we're going to get even a worse traffic jam, aren't we? So in this situation, because we have 2 barriers or 2 slowdown points, we're going to get a traffic jam, traffic congestion. So think about traffic on the 401. If there is construction where we have a lane reduction, the cars back up if we have 2 construction zones in a row, that makes the flow even slower. So that's the same idea. So here, as you can see, I have 2 barriers or resistors in a series. They're in a line. So they're going to cause a greater slowdown. So this is kind of an idea. So here, if we have no restrictions, the electricity flows no problem, actually, according to this diagram. So the electrons are flowing in this direction. But in this case, when we have a restriction, the tighter the restriction, the fewer that these can get through. So the more resistance we have in our circuit, the less flow we're going to get. So let's go back to our little diagram here. So what would happen if I add a third light bulb? With every light bulb I add in series, the worse the electric flow becomes. So instead of light bulbs, I'm going to use resistors. A little cleaner. So we add a resistor. So we've got the flow, add another resistor, and the flow decreases even more. So with every resistor I add, the slower the electrical flow occurs. Okay, so we're going to try something a bit different. So this is called a series circuit here. This is called series. All right, so let's clean that up. Now let's put our 2 batteries in here again. So I'm going to add this. All right, so I'm measuring the flow. So 1.8 amps. Now what happens? Now I'm going to add something. I'm going to add something different here. Now notice I'm actually building a secondary pathway here. And now I'm going to add one more resistor. Now I haven't connected the pathway yet, so I want you folks to think about this for a second. If I add this other resistor in this configuration, is this going to hurt or help our flow? And I'm going to give you an analogy. Going to the grocery store, waiting in line to check out your groceries, and then another new line opens up with a new cashier. Does that help speed people up to leave the store, or does it slow people down? And I think you know the answer to that. So when I add this next circuit in here, look what happened to the current. It dramatically increased. Now I have to clean this up a little bit. So now, why is this occurring? Well, let's think about it logically. Now, our kids in the water park have 2 pathways to go. They can either go down this route or they can go down this route. So even though we added another resistor, what we did is we added another path, a parallel path. And this is what we call a parallel circuit. So now let's add another parallel path. And when we add another parallel path, focus here on the current, and the current increases because we gave yet another option. So this is the difference between a series and parallel circuit. So in series, the electricity slows down with the more resistors that we have, whereas in parallel, the actual flow rate increases. So this is similar to the way multiple lanes in a checkout at a grocery store works, or this is very similar to the way a toll booth operates. We don't have too many toll booths. Well, we don't have any toll booths that I know of in Canada, but in the United States, there are toll booths when you drive on the highway. And the more lanes that you have, the more you can go across. I guess technically when we cross the border, there are multiple lines that you can get in for customs. The more lines that are open, the faster the flow. So again, let's compare that to a series circuit. So let's add the series circuit right above it. So here we are in our series circuit. So in this circuit, we have 3 resistors in parallel and the current is fast. Here we only have 1 resistor and the current is actually slower. Now what I'm going to do is I'm going to add another resistor, and adding the second resistor made this flow even worse. Let's add a third resistor. So in this circuit, every resistor we add in series makes it worse. Whereas in this circuit, every resistor we add in parallel makes the circuit faster. So here, the analogy, traffic jam number 1, traffic jam number 2, traffic jam number 3. The more traffic jams we have, the slower the overall flow. Well, in this version, this is like your toll booth or your supermarket checkout. The more lanes that open up, even though each lane is slower, is a bit of a slowdown, the more lanes that you have, the faster the overall service is going to be. So the more lanes we have, the more people or electricity we can accommodate. All right, so let's take a little recap here. So over here are the symbols. So the thing that measures the voltage, and remember the voltage is called the electric pressure, right? Is basically a circle with the letter V in it. The thing that measures the current is something called an ammeter. The reason why it's called an ammeter, it's actually related to amperage, which is named after a French scientist, Ampere, who worked with electric current. So we use the letter A, and that's why we have the letter A for amps. It comes from ampere. A lamp looks like this. A resistor is this little squiggly line. This is a conducting wire, and conducting wires we consider not having any resistance, and this is an electrical switch. Now when you look at the switch here this isn't specifically an open switch. With an open switch, that means the electricity can't flow because there's nowhere to go through. So this is like, imagine a bridge, a drawbridge. If the drawbridge is up, no cars can get across. But if the drawbridge is down, i.e. a closed circuit, then we're able to flow. This is a single voltage cell, and it's usually about 1.5 volts. And the long side is the positive and the short side is the negative. If you think about it, the short side kind of looks like a negative sign. And a battery made up of several cells. So in this case, that'd be 1.5 plus 1.5 plus 1.5 plus 1.5. That would be 6 volts there. Now some other ideas here. The volt, V, is measured in the units called volts or joules per coulomb. So a volt, voltage is measured in as 1 volt, which is equal to 1 joule per coulomb. Now again, what is a joule? What is a coulomb? Joule is a measurement of energy, just like calories is a measurement of energy. And coulomb is a measurement of the number of electric charges, right? Coulomb is kind of like an analogy to the liter for volumes. So a coulomb represents a certain volume of electric charge. Ammeter measures current, and the symbol for current is I, and it's measured in amps, which is coulombs per second. So this is a flow rate. So think of coulombs like a volume, like liters, and per second. So basically it's a measurement of electric speed. And the resistor is a capital R, and it's measured in ohms, which looks like the Lululemon symbol. It's not. It's the Greek letter omega. So resistance represents an impediment to the flow of electricity. So generally speaking, larger resistors slow the flow, smaller resistors encourage flow. So these things are related, and they're all related by something called Coulomb's law. My mistake, sorry. Not Coulomb's law. That's a little bit of grade 11 content. This is Ohm's law. And this says that the voltage is equal to the current times the resistance. Well, actually, the original version of this is the resistance is just the ratio of the voltage that we have divided by our current. Let's go back to our other diagram over here. So if we take a look here, each individual, let's take a look at this circuit, and I'm going to get my voltmeter. Oops, look, I measured it backwards because the negative side is supposed to go on the negative side and the positive side is supposed to go on the positive side here. Okay, so this is 18 volts. So the resistance is actually equal to whatever my voltage is divided by my current. Okay, well, my voltage in this case is 18, and my current, is equal to 0.6. Let's see what my overall resistance is. My overall resistance is 30 ohms. All right, well, let's take a look at each individual resistor here. This resistor is 10 ohms. This resistor down here is also 10 ohms, and this resistor down here is 10 ohms. Do you see how they're in a series with each other? So this is 10 plus 10 equals 20 plus 10 equals 30. So we have 30 ohms of resistance, which makes sense because the overall resistance that we calculated is 30. Okay, well, let's take a look at our other circuit. Now, in this case, our resistance is equal to our voltage. Now, I'm actually going to write a subscript here. The T stands for total. So we got the total voltage divided by the total current. Well, the total voltage here, and remember the voltage is the amount of electrical pressure, 18. But holy smokes, our current is really fast. It's 5.4 amps. So we get 3.3 repeated. So what's happening here? Why is it 3.3 repeated? Because each individual one of these is equal to 10. Well, basically, this is what's occurred. Watch what happens if I break this apart. Now look what happened to the flow. We have two resistors in parallel. I'm going to recalculate this with only the two. So that's 18 divided by 3.6. And now that's 5 ohms. Huh, interesting. So that's actually 5 ohms. That's equal to 1/2 of 10 ohms. So when we added a second resistor in parallel, we didn't double the resistance, we cut the resistance in half. So let's put that other resistor back again and look at the number this time. So that was 3.3 repeated. Well, if adding a second resistor cut it in half, adding a third resistor should cut it into a third. So 10 divided by 3, lo and behold, that's 3.3 repeated. Guess what would happen if we added a fourth? If we added a fourth in the series, it would make it 4 times as bigger, and in parallel, it would make it a fourth. So if we were to add a fourth one, 10 divided by 4 is 2.5. All right, so let's see if our prediction works out. So our prediction is if we add a fourth one, that should be 1/4 of 10 ohms. Well, that's our prediction. So let's see if our prediction works out. So let's add a fourth resistor. All right, adding our fourth resistor, our current has now increased to 7.20. 18 divided by 7.2, 2.5 ohms. So there you have it. Okay, so here we go. So what I'd like you folks to do for work today is I'd like you to draw these examples here. And that's it, folks. More to come.